So before we get into the questions, this workshop is actually sponsored by XCamp. So XCamp co-hosts this workshop, and later they'll be going over the trends and what's happening with USACO. And so what they are is a Silicon Valley-based institute that offers coding classes for middle and high school students. So if you find that you want to take more in-depth coding classes, maybe with smaller classes, then you can go over and check out XCamp's classes. So for the last 20 years, they've done Python, Java, and C++ classes, and they've provided a discount code CPI 100 if you're interested in checking out their website, checking out their courses. So in the meantime, we're going to get started with the first bronze question. As a reminder, bronze is going to be going from 10 a.m. to 10:45 a.m. PDT, but I'll give it to Evan.
All right, thank you, Melody. So let me share my screen right now. Give me a second. Hopefully you guys can see my screen. If you guys cannot, just say that you cannot in the chat. And so yeah, I'll be explaining the first bronze problem of the USACO Open contest, and I'm gonna give you guys the link just so that you guys can see the problem in case you guys want to. Yeah, the problem statement, even if you haven't read it, I'm gonna summarize it really quickly right now. The problem statement basically wants you to compute, given an even number of cows, find the minimum number of reversals of prefixes with even number of cows to achieve the maximum number of currencies at even positions. So in the input, they're going to give you a string and letters. Each letter is either a G or an H. So a G is a currency, H is a Holstein, however you pronounce it, I don't know. Let me get the laser pointer. And for example, this could be the input string. And as you can see here, I've numbered the cows from 1 to 16, and I've separated them into pairs, okay? And the cows are paired because you can only reverse prefixes with an even number of cows. So for example, you can only reverse the first pair or the first two pairs or the first three pairs or so on. Okay, now that we've separated them into pairs, let's take a look at what happens when we perform a reversal on a prefix. So first of all, for simplicity, let's number each pair of cows from 1 to n-2. So this is the first pair, this is the second pair, third pair, and so on. You get the idea. And for each pair, let HG, so for example, HG be equal to 0. So we're going to denote HG as 0. We're going to denote GH, so GH as 1, and HH and GG both as an underscore. I really should have named this 2, but you know, I guess it's fine. It's understandable in my opinion. So I will explain the intuition for letting HG be equal to 0, GH be equal to 1, and so on. But for now, just know that this string will correspond to this sequence of ones, zeros, and underscores. Okay. Oh, by the way, if you guys have any questions for me, if any of my explanation is confusing, or you didn't understand something, or I missed something, just tell me. I will answer that. And if we reverse the first 4 pairs in a string, this is going to be the result. So the highlighted parts, characters, highlighted cows are the cows that we reversed. So for example, we have HH, GH, HH, and then GH. And here we have HH, GH, HH, GH, which is this part reversed. I hope you guys get the idea. And notice here, of course, the ones, zeros, and underscores in this prefix also changed. Okay, and notice that essentially by reversing the first 8 characters, we first of all reverse the pairs without changing the order. So we put this pair over here, we put this pair over here, we put this pair over here, and we put this pair over here. And then we swapped every pair of letters, right? So this pair, after going here, we swap the 2 letters. So HH becomes HH, GH becomes HG, HH becomes HH, and GH becomes HG. In other words, if we're talking in terms of the ones and zeros and underscores, we essentially reverse the underscores, ones and zeros. So reverse the underscores, ones and zeros. So _1, and then we flipped every 1 and 0. So that's why we have 2 zeros instead of 2 ones. Okay. And here, let me explain further. So intuitively, 1 means there is a G at an odd position, while a 0 doesn't. So take a look right here. We have this pair, which is a 1, meaning that there is a G in this pair that is at an odd position, while the other one is not a currency, basically. And this pair right here, we have a G at an even position, and at the odd position, we don't have a currency. So that's why I named this pair 0, named these kinds of pairs 1, and the others underscore. You will see that, well, first of all, let me explain what this problem now reduces to. The problem now reduces to what is the minimum number of reversals needed to obtain the most zeros in the end. So in other words, what is the minimum number of reversals in the string such that the resulting characters of ones, zeros, underscores have the most zeros, basically. And notice here, because underscores never change after reversing, we can just remove them. Okay, so yeah, that's why we let HH and GG both be underscores, because even after reversing, for example, this prefix, the underscores or HH and GGs will never affect the answer, never affect the number of currencies at even positions. Okay, so yeah, that's why we remove the underscores. And here, this converts into this string of letters, and this, after removing the underscores, this becomes 1100. So let the resulting bits be an integer array, A1, A2, A3, and so on. And of course, in this example right here, A will be 1100. So yeah, we basically converted into a string of bits, and the question, of course, is now this. So of course, we need to map out a reversal in the original string and an operation in this sequence of bits. So let's define an operation. So an operation is defined as choosing an integer I, reversing the segment A1 all the way up to I, and flipping every bit in the range 1 to I. Okay. First of all, why are we doing this? Like I said, any reversal on the original string corresponds to an operation on array A, and also any operation on array A corresponds to a reversal on the original string. Okay, for example, a reversal on the first 8 characters will be equal to, first of all, reversing all the characters and then flipping all the bits. Okay. And here, let's notice that it's always possible to make array A consist of all the zeros using just operations. This is pretty intuitive. For example, if we have array A like this, we can first flip do an operation on the first 3 bits. It will become this. Do an operation on this prefix. It will become this. Do an operation on this prefix. It will become this. Do an operation on this prefix, and it will become this, and do an operation on the entire string or array, and it will become all zeros. Okay, hopefully it makes sense up to this point. So now let's append an extra 0 to the end of A, except we cannot perform any operation that includes the last 0. You will see in a moment why we did do this. So for example, this array of ones and zeros will become this. See, we appended an extra 0 at the end. And let's define C to be the number of pairs AX plus 1 such that AX does not equal AX plus 1. So basically, the number of pairs that are different in here. If you still don't understand, we can take a look at this. C in this case will be 1, 2, 3, 4, 5, 6. Okay. And we appended an extra 0 to the end because if we achieve C equals 0, then all bits will be equal to 0. Okay, and yeah, so basically, you guys can notice that if C bigger than 0 is true, if and only if we can perform additional operations to achieve more zeros in array A. Okay, so while there are pairs of bits that are different, we can perform an operation to make C smaller. Okay, so we're almost done here. Let's now prove 2 claims, and then we are going to be basically done. So claim 1 is, it is always possible to reduce C by 1 when C is bigger than 0 using exactly 1 operation. Should be pretty clear now. So consider the smallest x such that, ax does not equal ax plus 1. If we perform an operation on 1 all the way up to x, we will reduce C by exactly 1. So if we perform an operation right here, C will be reduced by 1. Okay. So yeah, that's claim 1. Claim 2, it's pretty long. If you don't want to read it, I'll explain it intuitively. So claim 2, it is never possible to reduce C by more than 1 using 1 operation. So for example, if we have an array A right here, and we do an operation on the yellow segment, all of the elements so the number of pairs that are different in the yellow segment will not change after the operation, nor will the number of pairs that are different in the green segment change after the operation. The only pair that can change from being different to the same after the operation is this pair right here. So we cannot reduce C by more than 1 using 1 operation. You can read this if you want to. Basically, it's a summary of what I said, or it's a longer explanation of what I said. But yeah, I like the summary more. You can read it if you want to. So yeah, after proving the first claim, the second claim, and noticing that it's always possible to reduce C until C equals 0, we can say that the answer is simply C in the end. If you guys have any questions, of course, ask me. The explanation is a little bit long. I know some people might like the intuitive explanation more, but yeah, I like the formal way more. So yeah, that's the solution. Let's take a look at the code. My code is right here. Let me show you guys the link. So I wrote in all 3 languages. You can take a look in your favorite language, but basically this is the implementation of my solution. So in C, this is C++, obviously. We're gonna first of all take an n, and we're gonna let answer equal 0, the minimum number of operations, right? And p equals -1, so p is the previous bit. So for example, in our slide here, so for example, if we are looping, give me a second, if we are looping through the character through array A, if we're right here, then p will be the previous bit, which is equal to 1 in this case. So yeah, and we are going to iterate through each pair of letters. So from 0 to n-2. In each iteration, we're going to take in 2 characters, x and y. Okay. If x equals y, then the corresponding character will be an underscore for these 2 characters. So we continue. We ignore this. Otherwise, if x equal to g, that implies that y is equal to h, right? They cannot be the same. So then we check whether p is basically different from our current bit. So if x equal to g, that means that ai will be equal to 1. So if p, the previous character, is not equal to 1 and is not equal to -1, we add 1 to answer, right? We want to find c, and we let p equal to 1. Otherwise, if p does not equal -1 and p is not 0, we add 1 to answer, and we let p equal to 0. In the end, the last character might be 1, which means that p equals to 1. We add 1 to answer in that case, because remember, we appended a 0 to the end of array A, right? So yeah, that's the solution. If you have any questions, again, you can ask me in the chat, but I don't see any questions, so I assume that you guys understand this stuff. So yeah, I'm now gonna pass on to the next presenter.
All right, hi everyone. Hi Kevin, just a dude in gold. So I'll be doing bronze, problem 2 and problem 3. So all of you can You guys can see my screen, right? Just give a thumbs up or something. Melody, can you see my screen?
Yep.
Okay, cool. So bronze problem 2 is, it can be explained in like 1 or 2 sentences. So you're just given a bunch of upper lower bounds, and they ask you what's the minimum number of them to be removed so that the bounds are all consistent with each other. So you can't have a lower bound to the left of an upper bound. Wait, sorry. You can't have a lower bound to the right of an upper bound and vice versa. And that's it. That's the whole problem. You have 10 to the by the way, this has to be something like some linear time and login time, something around that. Oh, Melody, could we share the slides? I mean the slides or the solution code? Melody, could you share? All right then. It's in the chat now. So a possible solution would be to check all 1 billion possible positions of Bessie and see how many bounds would be made invalid. And that would be 1 billion times 10 to the 5th for each run. That would be 10 to the 14th. I don't know about you, but my computer isn't that beefy. And USACO's grader definitely isn't that beefy either. Our computer would die. But here's the thing. If this, by the way, is the sample test case. And this, if we check here, if we look at this diagram, we can see that this entire area, hold on. Yeah. This entire area marked in yellow, it gives basically the exact same answer. All throughout. It doesn't matter where you select in the yellow, only this greater bound will always be made. This bound, one of these bounds will always be, the same bound will always be made invalid. Same ditto for this and this. Like they always give the exact same answer. So given this, we can see that we're just checking a lot of redundant positions. So wait, how do I clear the thing? Oh yeah. Clear. All right. So, wait, crap. So here, if we use the sample case with this cow, once again, these positions, we're checking a bunch of redundant positions if we're going through all 1 billion. And so if there was a way to just jump from each interval to each interval, which there's only around 10 to the 5th of, which is only around 10 to the 5th, then we can solve this problem in around linear time. So, wait, crap. Wait, sorry, I'm bad. There's only 1,000 positions. So I don't know what I'm on. There's only 1,000 positions. So if we only check 1,000 of these areas and we go through all the bounds for each time, then that would be n squared, which should be fast enough. By the way, I think there's a way to solve this problem of linear time, but it isn't required for this problem. So this leads us to our solution, which is to iterate through all positions of cows. For each position, we test how many bounds need to be removed. So specifically, we iterate through all bounds that are given. So if there's a G bound that's to the right or an L bound that's to the left, it needs to be removed. And that's basically it, we win. So the code naturally follows. I'll share it with you guys. Yeah, using 2 pointers, it's possible. Oh, no effect, but this is bronze. You guys don't have to know that. So I'll go to the C++ solution because I think most of the people here made C++. So this is just reading in the IO. This is a list of the greater bounds, and this is the list of the lesser bounds. This set here contains the set of all the positions that could possibly yield different answers. And so we just iterate through all the positions here. This variable tracks the number of cows that need to be lying for this position to be valid. And then we go through all greater bounds and all lesser bounds and check if each of them are valid. And if it isn't, then we increment the counter. And then this is just updating the answer, and we output it in the end. So very simple and elegant problem. Does anyone have any questions about the solution or implementation? No? All right, then I'll be moving on to the next problem then. By the way, you can always ask me questions about the previous solution. So if you still have a question, don't worry, you can still ask. All right, so this is the bronze P3 problem. We have 10,000 different types of metals. Each of them we have around 100 units. There is some existing stock, but we want to craft 10 of the last metal and the last metal only. And each metal can be crafted from previous metals and previous metals only. And they just ask you what's the maximum amount of the last metal we could get. So first, it might be tempting to start from metal 1, craft a bunch of that, go to metal 2, craft a bunch of that, and then inch our way to metal N. But that's really hard because we won't know how many metals are needed in the future. Perhaps we need a ton of metal 6, but we didn't craft a lot of metal 6. How would we know how much of metal 6 to craft? And the more you go into this rabbit hole, the more you realize that this method is just hopeless. So what if we started from metal N and worked our way back instead? So for many problems, the key is to think in reverse, unless you're called problem 1 during this contest. Thinking in reverse sometimes gives you the same problem, but sometimes gives you a much easier problem. Sorry, so there's a typo here. And so let's try starting from metal N. And if we start from metal N, we'd have to consider all of N's ingredients and then the ingredients of those ingredients and so on and so forth. So from that, it seems like we need to use recursion. I think there is a way to do this iteratively, but it's just much easier to do this with recursion. And so yeah, we do a little recursion. Code is here. I'll paste it in the chat. So this solution uses global variables for simplicity. I know it's not best practice, but hey, as long as it works. So we start at the final metal type, once again, metal N, and then we work our way backwards, and we take and craft the ingredients as we go along. And note that we always need to it's always best to take from the existing stock of an ingredient before crafting it because it makes the most sense. And if we can't craft a metal, well, either because its ingredients are gone or just because it doesn't have a recipe, we just give up. And the complexity is O of the sum of all the metal we have, which is 10 to the 4th times 101 million, which definitely runs in time, except if you're Python, because you're very slow. And the implementation follows. Yep. So once again, let me scroll down to C++. So this is the recursive function. So by the way, this is where we read in the input. It's very natural. We just read in the ingredients, the output type. There's some simple input validation as well if you want to debug it yourself. And this function here, if we can craft a metal, as this comment says, this function returns true and removes the used ingredients from this vector here. It just decrements the ingredients that we used. And if it can't, then it just returns false and doesn't use up any of the metals here. So if we don't have a recipe for this metal, we have to take from the existing stock or we just can't craft it at all because there's literally no way we can craft it. And then this is where we take from the existing stock, and here's where the recursion happens. We go through each of the ingredients that are used in the recipe, and once again, we take from the existing stock if possible. Actually, I think this area is kind of redundant, but it doesn't matter. And if we can craft it, then we return true. then if we can craft all of these, then return true. If not, we can return false. So the Java code follows pretty much the exact same logic. So are there any questions about this code? I know recursion is a bit tricky to wrap one's head around in the first place, so please don't hesitate to ask questions about this implementation. All right then, that's all 3 bronze problems, I believe. We still have 15 minutes left, so I guess we can start early. You can still ask questions though, I'll still be on standby. Evan and I will still be on standby to answer any questions you guys might have about the solutions or the implementations. And yeah, there's that.
So since the time listed on the website was 10:45, we're gonna take like a 15-minute break, and then if you have any questions, just message in the chat. And then at 10:45 PST or whatever other time you're in, we'll start the silver questions.
So now I'm going to be studying the silver solutions. So I'll start off with problem 1. Okay. I'll also send a link in chat if you want to do the problem. Okay, so essentially we're given n cows who want to visit each other, and if cow I can visit cow like A to I, or like the cow buddy, they're going to move some amount of times. But if that cow has already left to see their cow buddy, then they can't visit him and he won't move. And then they're going to visit each other according to like a permutation, which specifies order that they're deployed to see each other. And then we want to find the maximum number of moves that can occur if we choose the best permutation. Okay. So we should probably think about the conditions that make it so that some cows like won't leave their barns to visit their cow buddy because they've already left. So the question is kind of like already giving it to us as a graph. So we should probably think of it as one. So so we're just gonna look at the cows as nodes and then make the cow I want to visit as directed edges from like I to cow E to the I. So the sample input would look something like this. So cow 1 wants to visit cow 2, cow 2 wants to visit cow 3, cow 3 wants to visit cow 4, and cow 4 wants to visit cow 1. So if you draw them as the directed graph, the graph will look like this. Okay, so note that like in this graph, if we start at like node 1, then we go to, let me turn on my laser pointer. So you start cow 1, then go to cow 2, cow 3, and then cow 4. Wait, yeah, this is 0 indexed, but like if we go all the way to like cow 3, then we can't satisfy this edge of 40 because 0 has already left. And then this is true for like any node that we set at. It's like if we set at 1, we can't get this node here. If we set at 2, we can't get this edge here. So so in this sample input, we need to remove one edge to make it so that so that we can go through every single edge without revisiting any node, and we'll just call this like a happy graph. Yeah. Also, note that this graph is a cycle, or that like if you continue along this path of 0, then it's just going to go back to 0. Okay, so let's try to like generalize like this cycle thingy. So if we draw like another graph with a cycle, you'll note that like if we start at 0, then like we can't get the edge from 2 to 1. And if we start at like and if we start at 2, then we can't get the edge from like 1 to 2. So we need to remove one edge between 1 and 2 to get another happy graph. So you can either have something like this or like this. And yeah, so maybe we still want to like remove a node. If we don't have a cycle, or we still have to like. So let's just check if a cycle means that we always have to remove a node, and then if there's any other formations where we do have to remove a node. Okay, so here we have 3 example graphs. So here we have a cycle here, and then we have to remove an edge here, because if we start at 5, they're not going to be able to get like 1 to 5, like same thing here. So we have to remove one of these edges. And then here we don't have a cycle, and then we have to and we don't have to remove any edges. And here we have to remove one of these edges. So between 3 to 2, 2 to 1, 1 to 4, and 43. And then note that like these won't always match up with sample inputs, because for each one, everyone will have like wait, every node will have one outgoing edge. So this isn't actually a valid input, but this is just like demonstration purposes. Okay, so it's definitely possible that like we missed an edge case due to like this input stuff. So let's think about this like intuitively. So if you have like a graph with a cycle, then a node that we start with must like always not be able to visit a cow that wants to visit it. So like if we start at 1 here, then they're not going to go do like 3 to 1. If we start at like 2, then like everything gets shifted. So we won't be able to get 1 to 2. And yeah, so note that in any cycle, we're always going to have a system like this. So we'll always have to remove a node. And yeah, like going back to like the previous slide, every node will have an out degree of 1, or basically it wants to visit one other cow. So if so 4 is always going to have another edge going back to one of these. So we're always going to have a simple cycle doing. We're always going to have a simple cycle in our sample in our input.
那 Apple 好了，那个 Apple 快好了。
I'm not sure what you said. Could you repeat that? Okay. If you want to ask a question, then you can drop in chat. But I think I'm just going to continue. Okay. Continuing on, if you have a cycle and we move an edge from I to J, then we can always just like form a directed tree rooted at I, since every node has an out degree of 1. Right? Because like if you have a simple cycle where like everything has like yeah, so we can always form a directed tree rooted at I if we move some edge I to J with a cycle. And then like intuitively, if you have a cycle, and then I'm just gonna go back to some input here. So if you have a cycle and we have to remove an edge, then we should probably move the edge with the smallest move value, because then we're like maximizing the moves. So in this case, we want to remove the edge between 0 and 1, and we'll have a move value of 20, 30, and 40. So 90. Also, just to mention, it's helpful here to not think of trying to find a permutation, but rather just like removing edges from the total. Yeah. Okay. Yeah. So if you don't have a cycle, then we already have a directed tree. So you don't need to remove any more edges. Yeah. And then we have exactly 1 cycle for every single connected component, because again we have like a functional graph. Okay. So for implementation, we can approach this in like 3 ways. So you could either do like a torus in here algorithm, which I think was described in the editorial. We could also do like a DFS and just like look for back edges, because after you go through a DFS tree, then any extra edges are going to form a cycle. Or we can also look for the maximum shining force. So this can be done like cross goals or prims, but I think this is out of scope for Silver. So yeah, for me DFS seems like most on par with Silver. So we're just gonna go do that, and then yeah, I'm going to send oops, I'm going to send like different like other implementations that we can go to in the chat so you can read about these on USACO guide. Also, I forgot to remove this, but like strongly connect this stands for strongly connected components. This is like you're like overscoping if you do strongly connected components, but basically yeah, don't worry about that. But if you want to read about it, you can go ahead. Okay, so here are like the three. I think I'm just gonna copy paste this entire thing. Okay, but here are like three implementations if you want to go do them. So I'm just gonna go do DFS with backtracking. But if you want to redo any of the other implementations, you can do it. You can do so as well. Okay, going to C++, and here we're gonna have a recursive DFS. Yeah. Okay, so this is just gonna be a this is just reading an input, and then we're making all of these zero indexed. Yeah, and also note that in here we're totaling all our moves so that instead of having to calculate like all the moves after we're moving the edges, we can just subtract the edges that we move. And then here we're just gonna go through all connected components. Here we're going to have like some sort of like bug keeping. So this is just gonna be like unbugging. So okay, so visited value of 2 means that we've already like visited everything. So if you visited this already, then we're done. So just return. If visited equals 1, then it means that like that means we found the cycle. So we're just going to traverse we're going to backtrack to the cycle and then just find the minimum value. And here we store like the parents because we have like functional graph. So if you store the parents, we can just like go back through the cycle until we reach back to a root node. And then here we can go through the entire cycle. And here we just update the answer on spot. Okay, yeah. And then we're going to set the visitor of the current to 1, meaning that if any of the edges that we go to in the future loop back to this one, then it means that we have a cycle. And we're also going to set the pin for this. And then we're just going to DFS on its body. And afterwards, we're going to set visitor of current to 2, meaning that like we're done with this node. Yeah, so we're going to go do this for every connected component. We're just going to output the answer. And yeah, I think that should be about it. Does anybody have any questions? Okay. If you want to, you can always put any future questions in chat. But otherwise, I'll pass it to the next instructor, which I think is Jesse. So, yeah. Okay, sorry. I meant Nikhil.
Yeah, okay, yeah. Actually, I am the next instructor. Wait 1 second. Can everybody hear me? And is my camera working? Is that better?
I think your mic is like kind of quiet, so probably like go close to your mic.
Camera, yeah, I'm not sure why my camera is not showing up. 1 second. Okay. I guess. Okay, I guess camera won't be on today. Okay. So yeah, so basically I'll be talking about the silver problem 2. I will go ahead and share this screen. Everyone can see it? Yeah. Okay. So I'll be talking about silver problem 2. First of all, let's see the problem statement. Okay. So you're given two strings S and T. So S and T are just the names that we give the two strings of length N and M. So S is of length N, T is of length M. And N and M are both between 1 and 10 to the 5. Okay. Which contain lowercase letters between A and R. Okay. So each of S and T contain only lowercase letters between A and R. You're also given Q queries. The number of queries is also less than 10 to the 5, each of which also contains letters between A and R. Okay. For each query Q, print Y if the following condition is met, otherwise print N. Condition is when S and T are limited to only the letters appearing in Q, are they equal? Okay. So note important thing is that for each query Q, it only contains the letters A through R, and this also means that none of the letters are repeated, and it's also guaranteed that the letters are sorted. Okay, so basically that means that Q has max length of 18 because there's 18 letters between A and R. So the longest possible query can be like all letters between A through R. Okay. Let's see an example. Okay. So these are our S and T. So we have A, B, C, D and C, A, B, D. Okay. So we are given these two. We are given 4 queries. First query is only A, then AC, then ABD, then ABCD. 4 query answers. So basically the expected output should be YN, YN. Let's see explanation for each of the queries after limiting, right? So we want to limit S and T to only the letters that appear in the query. We get these ST pairs. So for query 1, so this is only A, right? We get S becomes A, S becomes AA, T becomes AA, right? Because for query 1, if we limit S to only the A's, we basically cross out BCD. And if we limit T to only A's, we cross out CBD, right? So we're left with AAAA. So for query 1, we have to compare. Are these two equal? They are equal, so the answer is yes. Okay. Now, query 2. By the way, can everybody see the red marking that I'm making? Just okay, yeah. So query 2, the query is AC, right? So once again, we limit to only A and C. We cross out B and D, and we cross out B and D, right? So we're left with S becomes AAC, and T becomes CAA, right? So we compare these two. They are not equal, so it becomes N, right? And similarly, you can try yourself, but it becomes AABD, AABD for query 3. So this is a yes. Query 4 keeps everything because ABCD. And you can see they're not equal, so the answer is no. So does anyone have any questions about the problem statement? No? Okay. So let's move on. First, let's see the brute force, right? So the brute force is just for each query, just make a new SNT, which is the limited versions. Then you can compare these two strings. So let's build S prime and T prime that are the results of limiting S and T to the characters present in Q for each query Q. Then compare S prime and T prime for equality and print out the answer. Okay. This is a very simple solution and very brute force solution. However, it won't work, right? Because we have to see the time complexity. For each of the Q queries, we are performing max of n comma m. So this is like whichever is greater amongst n and m. We're comparing that many comparisons to generate S prime and T prime, and then another max n comma m operations to compare S prime and T prime for equality, right? Total time complexity will be Q times max of n comma m, because for each of the Q queries, we're doing this many operations. So it's Q times n comma m, or max of n and m, which means total number of operations in the worst case is 10 to the 5. So Q is max 10 to the 5. N and M are both max 10 to the 5. 10 to the 5 times 10 to the 5 equals 10 to the 10 in the worst case. And in order for our solution to work, ideally we should have less than or equal to 10 to the 8 operations. So basically, this brute force will not work. Okay. It might work for the very small test cases, but for most test cases, or at least the maximum length test cases, it will not work. Now, we need some sort of intuition to build a proper solution. The first thing we see, right? We try to break the problem down into smaller cases. The first smaller case is that for any query Q, if a subset that we call Q prime of the query Q does not meet the condition, then the entire Q does not meet the condition. So let's give an example. Imagine Q is A, B, C, D, right? Now Q prime, let's say AC, right? So if AC does not meet, if AC is failure, then ABCD always has to be a failure. Okay. And failure means like after limiting to only A and C, then does S prime and T prime match, right? So that's what I'm saying is a failure. So if Q prime is a failure, then that means that Q is a failure. And this is true for any Q prime. So let's say Q double prime is A, B, D, right? So if ABD fails, then also Q fails. And note, there are scenarios when Q prime does not fail and then Q double prime fails, or vice versa. So Q, each of the subsets are independent of each other, right? So if one subset does not fail, if one subset succeeds, still does not necessarily mean that the entire query Q succeeds, right? For example, if the query AD does not meet the condition, none of these queries ADF, ADFG, or ABCD will meet the condition, right? So it also works in reverse, because it means that if you have any small query, then any query that adds any letters onto that will also fail if the small query fails. Okay. This is our first intuition. And note, this property is independent of what S and T are. Okay, so with any S and T, um, the the property is still there, still is valid. Okay, that's our first intuition. Second intuition, contrapositive is also true. Contrapositive basically means, well, you'll see what it means. Any query Q will fail the condition if any subset also fails the condition. Example, query ABC will fail if any of the queries A, B, C, AB, BC, or AC fail. Right? So basically this means that if any of the subsets of a Q fails, then the entire Q fails. Note again, this property is independent of S and T. So from just these two intuitions, we can generate a possible solution. Pre-calculate solutions to all possible queries of all lengths, right? And then for each query, look up the answer, okay? So what this means is, before we look at any of the input queries, before we do that, we can already generate all possible queries, right? So all possible queries is how much? Basically, 2 to the power of 18, right? Which is around 2 times 10 to the 6, okay? 2.6 times 10 to the 6. Possible queries. 2 to the 18 possible queries, or approximately 2.6 times 10 to the 6 possible queries, right? So this is basically just all like strings containing A through R, letters A through R, right? So for each of these queries, we calculate, right? So we make S prime and T prime, and then we compare S prime and T prime, right? And then for each input query, we just match against that, and then see, and then like see the answer with that. So that will mean that when we're getting the input queries, we already have a table set up. So that's like O of 1 lookup, right? Problem is that if there's 2.6 times 10 to the 6 possible queries, and 10 to the 5 length S and T, so this will be still too much time, right? So it will still not work, because this becomes 2 to the 18 times 10 to the 5, which is greater than 10 to the 10. Okay. So we still need something better. Intuition number 3. Yeah. Building on top of intuition 2, we can see that we only have to consider subsets of length 2 and length 1 to check. Okay. Why is this? Because all the subsets of the query which are bigger than length 2 also follow the same property, right? So let's see an example. If the query is ABCD, then all subsets of length 3, ABC, ABD, etc., right, will also fail if any of the subsets of length 2, AB, AC, etc., fail. Okay? So this means that if any subset of length 2 fails, then the entire thing will fail. We don't need to check any subsets greater than length 2, right? And basically, subset of length 1 basically means just all the 18 letters A through R. We have to check these because that means that we have to count the frequency of the letter in S and T, make sure they're equal. So that's kind of a special case with query length 1, but we just have to check that independently. But basically the intuition is for query length 2, or query subset length 2. So if there's a subset of length 2, then and that fails, then the entire query will also fail. So that's our grand intuition. And once again, this property is independent of S and T. Okay. So from this, we can build a solution. So for S and T, pre-calculate the solution to all possible queries of length 1 or 2. So query of length 1 basically means all single letters from A to R. So there's 18 of them. And query of length 2 means all pairs of letters from AA to RR, which is basically 18 squared of them. 18 squared pairs is equal to 324 pairs. Okay. Technically it's not, because like we don't need to like see the order, but like this is bounding number, right? 324 pairs. Then for each query Q, take all subsets Q prime of Q, right? So each query Q of the input, take all subsets Q prime of Q of length 1 and 2, and check against the table that you have pre-calculated in the first step, right? So this is step 1, this is step 2. Step 2, right? And check against the table that you have pre-calculated. If any of these subsets are failure, then the overall query is a failure. Okay. And do this for all Q queries. So let's see an example, right? So if the query, if the input S and T is the example that we saw before is where is it? Example, yeah. So if the query, if the input is A B C D and C A B D, right? Then we first of all only need to check the letters that are inside the input, so A through D, right? So we take all of these pairs, right? So we have AA doesn't really exist, so we start with AB, right? So AB solution is yes, right? So AB is yes. AC is no. AD is looks like yes. Now we go to BD. So BD is yes. BC first of all. So BC is no. BD is yes. CD is yes. Okay. So these are all subsets of length 2, right? We don't count duplicates, we don't count repeats, right? And then we also have query of length 1, or subset of length 1. A is yes, B is yes, C is yes, D is yes, okay? And this is because the frequencies of all of these are the same. So there's 2 A's, 1 B, 1 C, 1 D in both of these S and T, okay? So now from this table that we have set up, right? For each query, we go through all the inputs or all the subsets and then check. Query 1 is just A. So just A, we have it here as yes. So it's just yes automatically. AC, only subset of length 2 is AC, which we already have no. So the answer is no. ABD. So ABD subsets are AB, BD, and AD. AB is yes, AD is yes, BD is yes, and A is yes, B is yes, D is yes. So we haven't found any no's. So answer has to be yes. And now ABCD, AB is yes, but AC is no. So once we hit our first no, the answer for the query already has to be no. So from this, right, we can calculate our answers to all 4 queries. And yeah, it's done. Okay. So final solution. Yeah. So this is final solution. Let's see the time complexity. So first step, go through each pair of letters, 18 squared pairs. For each pair, build S prime and T prime. So this is 10 to the 5 length. And we also have to compare S prime and T prime, which is also 10 to the 5. Second step, for each of Q queries, so there's 10 to the 5 Q, 10 to the 5 queries. Go through each pair of letters, 18 squared pairs, and look it up in the table. So lookup is 1. So the total is 2, because we have 2 steps that are like this, 10 to the 5 times 18 squared, which is approximately 6.48 times 10 to the 7 in the worst case, right? And remember, our ideal number of operations is around 10 to the 8, or sometimes 2 times 10 to the 8. So basically this solution does work, but very barely, right? So you can find my solution code here. Copy link, I'll put it in the chat. Note that Python is too slow. We're cutting the solution kind of way too close here. So that's why Python is too slow. And fun fact, I actually tried to make it in Java and my Java solution was too slow. So I just copied the USACO.org's solution for this one. But the C++ one, I actually made myself, okay? Yeah, so let's take a look at the solution. See how it is similar to what I explained. Okay, so we start with S and T. We take S and T as input. Have a Q, we also take Q as input. And we have this global Boolean pair works, right? So pair works is basically our like initial table of each pair between AA and RR, if it works or not. So we start that off as everything is true because we only set it to false once we see that it doesn't work, right? So first of all, this loop is checking for each letter. So for each individual letter, does the is that letter as a subset of 1? Does that work, right? That basically means that does the frequency of the letter match in S and T? Because if the frequency matches, then that query matches, basically. So I just get frequency of this letter I in S count and in T count. Then I store it in pair works at that location is equal to S count equals T count. So S count equals T count means that it doesn't work. And I store it in the pair works at that location. Next, I have to go through each pair of letters. So between AR to I plus 1. So basically I'm starting with AB, going all the way to not RR, but what comes before R? Q, right? QR. So yeah, I'm going up to QR. I have S2 and T2. This is basically S prime and T prime. First of all, I'm generating S prime by going through S if it's either I or J. So I and J are the two letters, right? So I'm basically limiting S and T to the letters that I'm checking, right? So if S S at X is equal to I or J, then S prime plus equals S at X. So, and doing the same thing for T. So now I've generated an S prime and T prime, and then pair works I at J is equal to S2 is equal to T2. So S2 and T2, I compare them for equality and then store it in the pair works. So now I have the table all set up. Now basically for each query, right? So while Q is greater than 0, Q string Q and C into Q. So take the Q as input. We have an answer starting at true for each. So first of all, we check each individual letter. If that letter does not work, then the answer is false. So yeah, so that's just one thing. And then now we check each pair of letters. So for each I between 0 and Q dot size, for each J between I plus 1 and Q dot size, because again, we don't really need the repeats. It wouldn't harm, but we just don't need them. If not, so if this pair does not work and the pair is the letter at Q at I and Q at J, right? So if this pair of letters does not work, then answer is false again. And if answer is true, then print out Y, else print out no. And I can is the sharing property correct? Everyone can see or like click the link to the USACO guide. Yes, okay. I understand why query fails if a subset fails. Why query have to succeed if all 1 and 2 element subsets also succeed? Okay. So this is basically there's no other possibility, right? So a query can only fail if a subset fails. Okay. And let's say we have A, B, C, D. This query can only fail if any of the subsets fails. Now the subset that fails can also be a 3 length one, right? So let's say let's go to a blank slide. Or yeah, so let's go to this line. Let's say the query is ABCD. Q ABCD. Q prime, let's say we see that the subset ABC fails, right? Now ABC fails also because some subset of Q of this ABC also fails, right? So we can keep on going down, right? So now one of the subsets of ABC also has to be failing, right? And let's say that Q double prime AB, this is the one that's failing, right? So that's why I said the property kind of propagates all the way down until the length 2. So we have so that's why like we only need to check the length 2 subsets, because if the length 2 subsets fail, then all the length 3 subsets that build upon length 2 subsets fail. Then length 4 also fails, length 5 all the way up to Q, all of them are failing. Okay. So that's why we only need to check length 2 and not length 3, 4, right? And outside of these subsets, there's no other possibility of fail, right? So if none of the subsets fails, then there's really no other possibility that of how the entire thing fails. William, did I answer your question, or are you still confused? Okay. William, thank you for the question, by the way. It's a good question. Does anybody else have any questions? Okay. So I think now the next instructor is Jesse. So yeah.
Can you guys see my screen? Okay, so basically this problem is called cow operation. It's the third solo problem. It's basically you're given a string of length n with only 3 characters COW, and you have to determine whether the string can be reduced down to a single C using one of the following operations for each of the q given queries. So you choose, so like each operation, you either choose 2 adjacent equal letters and delete them, or choose 1 letter and replace it with the other 2 letters in either order. So each query asks for the answer in the substring LR. So for example, like you might have like a string like COWC, and then like you over here you can change this to like a C W, and then W C, and then now you can like delete this and delete these 2, and you're left with a C here. So basically you can delete 2 adjacent equal letters. So like here I deleted the adjacent C's, and you can choose 1 letter and replace it with the other. So you can change the O into like a CW. So like the query, each query asks for the answer in the substring L comma R, and they're like 2 L and R are both like integers. And the rest of the solution, like it utilizes the fact that OW or WO can be turned into a C. And here's the sequence of operations. So OW can be turned into OOC because this W can be changed into O and C as shown by this operation. And then you can delete the consecutive O's like this, and then you get C. So okay, so basically here are the important observations. Okay, so here's like an example. So suppose we have an input string like WCO, COCW, COOC. So we can transform the string down to a C by the following operations: WCOCO, CWCOOC. We can delete these 2 O's right here, and we get this. And then now we can delete these 2 C's, and we get this. And then we can turn the C over here into WOs. And then after that, we can delete these 2 consecutive W's. And then we get this. Then we can delete these 2 consecutive O's. And we get this. And then we can convert this W here into a CO. And then once we do that, we can delete these two consecutive C's and then these two consecutive O's. Then we get our final C here. So now let's suppose we have an input string WOCOWC. And so we're left with string CC by doing the following operations. So WOCOWC. Now we can turn this into CO. And then we get this string. And then we can delete these consecutive O's right here. And then get CCOWC. Delete these two here. And then convert this O into CW. And then delete these consecutive W's. And we're left with CC. But after like doing a couple of other operations, we notice that this CC can never be turned into a single C. And you can prove this as an exercise. So okay, so now so based on the two previous examples, we can notice that we can reduce a given input down to a C if we get so yeah, we can't reduce a given input string down to a C. So we get this, like one of these strings, and there's no way to turn any of these strings down to a single C. So if we end up with one of these final strings, then the answer would be like no. And we also notice that we can turn an OW into a C. So we can consider each OW as a C. And the configuration of O's and W's and C's, they don't matter, since we can change the O's into CW's and C's into OW's and W's into CO's. So thus we can determine that the number of C's, O's, and W's can answer whether this given string can be reduced down to a C. So here's a solution. So like, let's say the input string, we have an input string C, C, O, W, O, W, this thing. Like this is sort of the optimal configuration because we have like multiple OWs, which we can like just convert them into C's, OWs here, OWs here. And we have like consecutive C's here. And then we have like trailing O's. So it's like sort of like the optimal configuration. And earlier we proved that like the order doesn't really matter because you can you can change the string down to like one of these by doing a sequence of operations, since the count of each C, W, and O is the same. So the number of trailing O's is 4 here, so we can completely just like delete these. And so we can only delete like trailing O's or W's, because this can also be like W, 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 if the parity of the count of O's or W's, like the trailing O's or W's, is even. So in this case, it's 4, so we can delete this down to like we can just like completely erase this. However, if it's odd, so let's say we have like O, 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 then we like if the parity of the trailing O's or W's is odd, then let's say we erase it like this, and we're only left with an O, and this is like we can't turn this into like, we know that O's can't be reduced down to C. So if the parity of the trailing O's is odd, then we can't change it into a C. Okay, so we also established that CC's can't be reduced down to a C. So for that earlier input string for this early input string. So once we delete all these O's, then we can, let's say, like turn all these OWs into like C's. So now we have C, 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 C. So now we notice that all these OWs, it can be turned to C's, and these C's can all be like reduced down to a single C. So the answer for this query string is yes, because total number of C's, like the parity of the C's is odd. So we established that the CC's can't be reduced down to C's, and so like this was like the final sequence of C's. So we can delete the first 4 C's that I showed and reduce it down to a single C. So only the last character after deleting all those C's matters, and basically like if the final string is like empty after deleting all the C's, then you can't reduce it down to a C. Otherwise, if there's like one final C, then the answer for that query is yes. So this is basically saying like the number of C's is odd after you convert, obviously after you convert all the OWs or WOs into C's. So now that we know how to determine whether a string can be reduced down to a C in O of n time by determining the counts of each character, we just need to be able to answer each query string in O of 1 time, and we can do that using prefix sums. So you can see my implementation. Can you guys see my code? Okay, so basically my code, you start with like reading in the input string and reading the number of queries, and then you count like each C, each O, each W using prefix sums, and yeah, so you have a prefix sums of like C's, O's, and W's, and then afterwards you read in the query, so like L comma R, and then you find like the number of C's, the number of O's, and number of W's, and then OWs, like the number of OWs is basically the min of the number of O's and W's, and then the trailing O's or W's is basically like the max of whatever it is minus the OWs, max of the O's and W's minus like the number of OWs. So now all we have to do is check if the count of C's is odd, and like if so if the count of the C's is odd and the number of like trailing O's or W's is even, then the answer is yes. Otherwise, the answer will be no, and that's basically it.
Okay, so that concludes the bronze and silver questions. Next, I believe we have XCamp presenting some of the new trends and updates for USACO, and then how to practice for the next seasons, and then the next couple competitions. So if XCamp wants to come and present.
Sorry, is that my turn?
Yeah.
Okay, so Let me share my screen. Okay. Today I want to share something about the USACO bronze and the silver context in recent 2 or 3 years. First, I reviewed the bronze contest in recent 3 years and the silver contest in recent 2 years. And first, I know you guys are interested in promotion, right? Once you get promotion, that means you get level up. You get to a higher level, and you can learn some more algorithms, right? So I think the targets you take part in the context is to get promoted, right? In bronze context, the promotion rate is about 15%. And the score is around 700 to 800. But I think it doesn't matter if the promotion score is 700 or 750 or 800, because you need to solve at least 2 problems, right? To get more than 700. And you also need to solve some of the subtasks of another problem. So that is for bronze promotion. For silver, the promotion rate is even lower. I was surprised when I know that the promotion rate is even lower than 12%. In some contests, it's lower than 10%. And the score is about 800, between 800 and 650. And the promotion score decreased by time. It doesn't mean it's easier to get promoted. It means the problems are get harder and harder. Okay. First, I reviewed the bronze problems and I just classify them. There are 4 major types of the bronze problems. The first is simulate. What means simulate? It means there is no specific algorithms or specific methods. You just write a code and do what the problem asks you to do. And so in many simulate problems are very easy. For example, I will show you like a very easy simulate problems like this one. Okay, so you just like group all the words and you group some of the words which the total length is like not more than k characters, and then you just output them. So this kind of problems could be very easy because it's broad level. So we have these very easy problems, okay, and some problems are greedy. The greedy problems is, I think, except the simulate problems, they are very easy, and the greedy problems appears the most times in bronze level. And also we have search problems. Search means brute force search. That is, you just search maybe all the possible cases, something like that. And also in the recent 3 years, we also have a DP problem in bronze level, but we only have one. So that means DP doesn't appear many times in bronze level. Okay, so how is difficulty in the bronze level? I think one of them is very easy, like this one. I just show you, and one is easy. Maybe you will spend some time on it, but it's not too difficult for you to solve it. And then the other one is a little bit hard. That is for the red problem. The red problem is a little bit hard. So, but how to promote? You just solve the easy problems and solve the subtask of the hard problem. That means sometimes there is a problem that is a little bit hard, but you don't need to solve it. Or just for promotion, you don't need to solve it. Of course, you can solve it for a 4 score, but if you want to get promoted, you don't need to solve the hard problem. You just solve the subtask of the problem. So what are the keys to solve the easy problems and even solve the hard problem in the bronze level? First, for simulate problems, you need to have basic coding skill. That means you read the description and you just code to simulate what the problem asks you to do. Okay, so I think it's a very basic coding skill. I think most of you have just passed this phase, right? And sometimes the problem description could be a little bit complex, so you need to understand it. You need to read it carefully and understand the description. And if you misunderstand the description, then it will be very unlucky for you. You will maybe get zero score in this problem. So you need to understand the description. And the second part is very important, I think, in bronze level. because the greedy problem appear many times, and the greedy problem could be difficult because in bronze level we do not have other algorithms like DP, very few DP problems, like data structure, no data structure, like graph. I think no graph in bronze level. So we only have greedy. So the easy problems may be greedy. The difficult problems may be greedy. So if you have difficulty to pass the bronze level, you need to learn greedy more. Okay, so how to solve greedy problems? I think first you need to judge if a problem can be solved by greedy. How to do this? Sometimes you need to do more. I think first you need to do more greedy problems, and you will find how the greedy problems is like. The greedy problems is like maybe the data range will be big, will be large, because greedy the complexity is very low, so the data range can be very large, like 1 million or like 100,000, something like that. And of course, there are many other methods to judge if a problem is a greedy problem. Okay, but I cannot say too much here because the time is limited. And the second is you need to know some common greedy method. The bronze greedy problems will not be too difficult. Most of them are very common method. So if you know the common greedy methods, then you will more likely to solve the bronze greedy problems. Okay, and the last one is the keys to solve difficult greedy problems. That is, you need to make assumption. What means make assumption? That is guess. So you need to guess. Sometimes because OI is not like math. If it is a math problem, then you need to prove, right? You need to prove your assumption. But if it's a OI problem, then you don't need to prove. You just guess, and of course you need to check. You need to check for some cases, and if you check some cases and you do need to prove. Okay, so for the difficult greedy problems, guess is really important. And then we have some search problems. The search problems in bronze is not difficult. You just need to know how to do search. Okay, the most practical search method is DFS. If you know how to do DFS, then you can solve most of the search problems. And the last one is geometry. In bronze, I saw many geometry problems like this one and this one. And I think there was one more I didn't mark it. Okay, so but it's very basic geometry, like count the area, like count the calculate the intersection of two lines, something like that. They are very basic. Okay, that's for bronze. And how to solve the hard problems in bronze? There are, of course, it's not easy. So I give you some suggestions. First, you need to know some common tricks or skills, something like that. What is common tricks? Like the Jensen difference or some other tricks to solve the difficult problems. And the second is decide what kind of problem it is. Like you need to decide if it's a greedy problem or it is a search problem. In bronze level, it's easy because there are few problem types, right? If it's not a simulated problem, then it will be a greedy or search, something like that. And then it's important to analyze the problem. Here we will find many of the difficult problems need to use some observation. So you need to analyze the problem and to get some observation. And the last one is sometimes you need some idea. So how to get an idea when you see a problem? I don't know, but maybe do more exercise will help you to get idea when you see a problem. Okay. And for silver, there are a little bit different from bronze because we have more types of problems. The first difference is we have many graph problems in silver, and the graph problems are even more than the greedy problems and the simulated problems. So there are the most graph problems are the most problems in silver. Okay, and we also have dynamic programming problems and data structure. And the difficulty for Slaver, I think it is the difficulty is increasing by time, even as difficult as the early gold stage. I think the silver difficulty this year, I think it's as difficult as maybe the gold 2018 or 2017. So it's become more and more difficult. One of them usually it's easy. but the other two are difficult. One is a little bit difficult, but the other sometimes it's a little bit difficult, but sometimes very, very hard. Here we will find 4 red problems. The 4 red problems are very hard. But if you want to promote, you just solve the easy problems and the one hard problem, and solve the subtask of the other problem. So you don't need to solve the red problem. That means you don't need to solve the very hard problem. So, sorry, this is silver. So what are the keys to solve silver problems? First of all, simulate. Also, you need to have basic coding skill and understand the problem. And for greedy, you need some you need to learn some advanced greedy method, different from the bronze level, because the silver level is more difficult. And sometimes for greedy, you need to apply with other methods like DP, graph, or data structure. Also need to apply greedy strategy in this kind of problems. And for search, you need advanced search skill like meet in the middle, in this problem. And for data structure, there are few data structure problems in silver stage. Only one here. But you still need to learn something like set, heap, monotonic tree, and segment tree, this kind of data structure. And the most important type is graph. You need to learn shortest path and like circles, connected components, connected components, something that the basic knowledge about the graph. And the last is the most important. That means you need to construct the graph. Some graph problems is like, okay, given a graph, or here is a graph, something like that. But most of the graph problems in silver stage, there is not a graph in the description. You need to construct the graph by yourself. That means you need to understand what is a graph and when we need a graph. So that's very important in the graph problems, that is to construct the graph. Okay, and then the last type is DP. For DP, you need to learn advanced DP methods like bit mask, digit DP, range DP, tree DP, something like that. And also, very important thing is to judge if it is a DP problem. So you need to judge if a problem is DP or greedy or search or something like that. Okay, so how to solve hard problems in silver stage? First, also, you need to learn some common tricks. And the second is very important, is to decide what kind of problem it is. Like, it's a DP problem or greedy problem or counting problem or data structure problem. So you need to classify the type of the problem. This is if you know the method to classify, it will be easy for you to decide what kind of it is. And once you decide what kind of it is, the problem will be much easier because you know the basic algorithm like DP or greedy or something like that. Then you can solve it more quickly. Okay. Of course, for hard problems, you also need to analyze the problem. You need to get some observation, and also you sometimes you need idea, and how to get idea. Okay, do more exercise, and that's my suggestions for you to learn how to learn the bronze and the silver stage problems to solve this kind of problems. And do you have any questions? Sorry, the titles are just wrong. Do you have any questions? Okay, thank you for listening.
And then I will be talking about some of the suggestions from USACO as well. Let me do a screen share. Can you see my screen? Hi, everyone. Can you see my screen?
Yeah.
Oh, okay. Thank you. Hi, my name is Yuan, and it's a pleasure to be here. I'm one of the co-founder of XCamp, and I want to take several more minutes just to talk about some of the pinpoints that we've observed from the students in XCamp this year. And also, I won't go into the detail as teacher Yizhong, but I will also provide some of the high-level suggestions as well. And also, I want to remind all of the students here that the next USACO season has already started. It's not like 8 months later, but it's already started. And in order to pass in December or next year, you have to start to prepare it for now, starting from now. So yeah, so for those of you who don't know XCamp yet, we are a programming and basically in general STEM institute based in US. And currently we have students in Silicon Valley, Austin, Seattle, New York, and Boston. And yeah, I want to start with some of the common pinpoints. So for many of you, like based on our experience with our students in XCamp, we saw cases like, I don't know how to prepare or what to learn for USACO. We also have lots of external students consulting with us regarding how to pass, right? So and also we saw students asking about solutions seem to be all feasible, but I cannot just figure them out in tests. right? This is, I'm pretty sure many of you also experienced that. And also I've learned all the relevant topics, but I just cannot pass the USACO levels. Those problems looks very different from the practice problems, right? This is also another common issue. And for some of you, you learned most of the stuff online on your own, which is really good, but probably you feel a little bit lonely and the lack of support, especially when you see bloggers. Probably you find it difficult to get some help from other people, either because they are too high level or maybe they are not in sync with you. They don't understand where you are, right? And for some of students, they practice all of past USACO tests problems, but still they cannot solve the medium level or hard level of the problem in real USACO tests, which is also a very common issue. And for some of students, even internally in XCamp, we also saw them, they really like programming and the problem solving. But as USACO became harder and harder every year, some after try for USACO for 4 times, they also got frustrated and they are considering quitting, right? And for many of students not in XCamp, this is even more common. And the most important thing is that for students who are on their own, they don't really know where they are and they don't know what to expect if they want to shoot for the next USACO seasons, right? So I won't be able to solve all the problems today, but I will provide some of the suggestions for you. And hopefully it will be helpful for you. For more questions, feel free to contact us after the event. In general, like for bronze, silver, gold, and platinum, even for camp, is very, very different, right? In general, I want to divide them into 2 categories. One category is about bronze and silver. In XCamp, we call it more of a knowledge level, right? Meaning that once you finish the topics, you do the homework, right? You do some of the actual practice. Sooner or later, you will be able to pass. So in XCamp, or in general, we don't recommend you to focusing on passing these levels as the only goal. Instead, we want you to focus on learning the topics, because these topics it's not because of a USACO they are useful. It's because they are the foundation of the computer science and they are the foundation of the, in general, software industry. That's why they are so important, right? Just like those fundamental algorithm and data structure. And in general, we would recommend students to focus on learning and building systematic knowledge system, right? So, but over here, learning online, of course, is something that many of you do. And recently we found the CPI backed USACO guide to be really, really useful as well. It's definitely some good resource that you want to take advantage of, right? And in general, you want to use a very structured and proven and approved curriculum to save your bandwidth, save your time, right? And in the end of the day, please do not worry about, I want to pass bronze this time, or I want to pass silver next time. Please try not to do that. Instead, try to focus on learning and improving ability in this level. The reason is that as long as you grow in your knowledge, you will pass sooner or later as you stack more experience, right? Okay, so this is for bronze and silver. Again, they are mostly about knowledge. But for gold and platinum or even camp is very, very different, right? Because all the knowledge, all the topics covered is way far away from the destination. It's, in general, it's just the starting point, right? For those of you who have learned all those advanced algorithm and data structures, you just hit the starting point, right? So in general, the reason why you found those real USACO problem to be much harder than practice problem is that if you are the problem composer, you don't want to repeat those practice problems, right? So if you are the people who make those problems, you want to avoid repetitions and you want to find out some weak points for the contact for those of you who participate in USACO tests, right? So yeah, it's just like a hunter and a huntee, right? So basically over here, you want to over prepare for much more variations and checks than the classic ones and the fundamental ones, right? And in general, we found last year and this year, gold, platinum to become harder and harder, and those checks becomes those of the checks that less frequently to appear, right, in the past. So that means you need to be able to solve lots of hard questions in order to unblock yourself, in order to get comfort in tackling those problems in real competitions. Okay, and the last, which is also the most important thing, is that you want to have lots of real competitions, serious competitions, to polish your skill in all the dimensions. My personal recommendation would be 3 to 4 real serious tests per month at least, in order to get you always active in this area to maintain the muscle memory, right? And most importantly, you don't want to leave those hard questions in those tests behind. Please absorb all the hard problems of the tests. That also means that those problems appearing in these tests need to be well selected and need to be the right problems for you, right? Sometimes it's too hard, then it will frustrate you. Sometimes it's too easy, then it doesn't become effective to improve your ability, right? Okay. So again, for gold, platinum, camp, have the knowledge, have the topics covered first, and try to do it as fast as you can. And then after that, you will need much more bandwidth spent in hard problems and in mock tests, and you want to do it on a daily basis and fully use your summer and your winter to do it, right? And if you're shooting for the next season, I highly recommend you to start right now, okay? Yeah, so I just want to take 1 to 2 more minutes to talk about what XCamp can offer in the whole USACO ecosystem. So basically, to pass bronze or silver, we have a very structured and proven curriculum that we've already lifted hundreds of students to pass USACO different levels, right? And we do have around 20 students in planning as well who are preparing for the US camp, okay? And we mainly focus on algorithms and data structure, as I mentioned, and we focus on improving your abilities, not passing some certain levels in USACO, because USACO is not the only goal here. We want you to get prepared for industry and for academia when you graduate from college, right? Also make your college life much easier if you are in some engineering-based major. And to pass gold and platinum, we have all very, very experienced coaches who are NOI medalists. NOI is basically a national, just like USACO in China. And for ROI medalists and also ICPC world finalists. ICPC basically means that it's national college programming competition, right? And in this level, we not only teach topics, which is the minimum requirement, we also push you in the right direction, and we help you to unblock anything along the way. And a very special thing in XCamp is that we have very dynamically adjusted hierarchical classes, meaning that we will push you and we will move you to a higher level of class to team up with people who are excellent with high commitment to compete together. And in this process, we want you to have peer pressure. We want you to have support from peers, from the coaches, right? And in general, it will be a very competitive program, very competitive environment. And we believe only with that environment, you'll be able to have lift your skill, improve your experience as well, right? And the last thing, which is I also personally think which is really important, is that will help you to resolve any blockers, small or big, We talk to you about your psychological blocker. We talk to your parents to help you to get more room for practice, right? I mean the room, the abstraction, right? And also we help you to do customized directional suggestions, right? And basically, the only thing you have to worry about is that you need to be committed and work really hard. We make everything else easy for you, but we want you to be committed and work hard. And there's an email here. And if you can help us spread out the words, that would be nice. Thanks. And regarding the format, we support both online and in-person classes. But in-person ones are not completely resumed due to COVID. And we have both weekly class and we have very intense camp in the summer and winter break to really boost their levels, right? And yeah, there's an email there. There's a very quick snapshot of the class structure, which you can also get from our website. And that's all. And if you have any question, this is the right time to ask. Okay, I will first stop my screen share. Yeah, Melody, back to you.
Okay, so our workshop did run a little bit long, so I think we can just end it here. If you have any more questions, feel free to contact XCamp or feel free to look at other CPI stuff. We have the USACO guide, and thank you all for coming.